So let's see a problem on VLIW. So our first question is, given this particular program, we have to perform a VLIW instruction set. Like we have to issue two memory references, one floating point register and one integer operation. So a particular issue will contain 4 instructions in every clock cycle, and we have to make sure, like we have to issue this to a processor in such a way that it should have no stalls, and we are asked to unroll it for 4 times, and they have given the latencies also. So let's first see how to unroll the loop first. Okay, so given before that, we will just for a simplicity, we will write whichever instruction is using whichever registers, so that it will be easy for us to note it while unrolling. So first instruction is LD. I'm going to write only the return register, that is after the operation is completed, what the value will be written in which register. So LD will be writing it in F2, and my multi is reading from F2, so which is already here, and F0 is fixed, so we have to make sure we note that one also, so that we don't use while unrolling. So fixed is F0, and multi is writing it in F4. Okay, and another multi is issued, and multi is writing into F10. It's using F4, which is from the previous multi, so it's already there. And F8 is fixed. F8 magically F8 came, so somehow in previous lines of code F8 must have been loaded, so we should not touch F8. So we should make sure we do not use F0 or F8. And again another load is there which is saying F6, so it's going to write into F6. Now we have an add instruction, so add D, it's writing into F10, and already it's loading from F10. It's getting its value from F10, which is already loaded, and F6, which is already loaded, so we don't have any fixed values here. And then our store instruction is writing it from the F10 value. And store, I'm going to for only store I'm going to see which is the source operand. For rest of the thing I will see what is the destination operand. Okay, so for easy purpose we will write it here. Now also they have given, like we have to assume this much latencies for each and every instruction. Say for example, for accessing a floating point instruction, result from a floating point instruction will take 3 clocks. We will see how this affects us in the construction of our VLIW issue. Now for first purpose, like we will unroll the loop first. So we are asked to unroll the loop for 4 times. So we will unroll it now. First unroll, we'll just blindly write it as whatever is given in the question. So load F2, 0 of R1, then multi F4, F2, F0, then another multi F10, F4, F8. Then we have a load D, which is F6, FR2, add D, F10, F10, F6. Then we have a store F0, R2, F10, and then since we are unrolling, we will obviously, this is the loop finish up code, that is we have to adjust our memory pointers so that we can access the next registers. But we are unrolling right now, so this fix up code is we have to write it after the 4th iteration only. So we will write the next iteration. We have the load again. In the load, since while loop unrolling, we have to have enough number of registers. We know MIPS has 0 to F0 to F31. We know that MIPS has F0 to F31. Now we cannot use F0. F0 register is always set to 0. We don't have any permission to write into F0. So for user purpose we have F1 to F31. We should always remember that one also while unrolling the loop. Now the easiest or the smartest way to do is now is to give it as a 10 offset. Say for example, you can write it as F. Say we can put it as F12. We are giving enough number of registers. See here it is F10 is used here. We can use F3 also. You can put F3 here, but using like this as a random thing, like, or a sequence thing, you have to remember where and all we are using it, and where we have to keep track on a lot of places. So easier way to do is to add blindly 10. Just blindly add 10 and put it. But this will again cause an issue. We will see how it will cause and how we can resolve it. So we'll blindly add 10 to the F registers. R is fixed already because R is already been loaded. We are not loading in the program, so we should not change the R value. But this 0 is saying like R1 contains some address and we have to access with the 0 offset, that is accessing the correct that particular address. But we are not doing any fix-up code here. The fix-up code is saying add 8 bytes to the R1 register and access it. So we have to make sure that we have to add that 8 bytes and then call the address. So while unrolling, make sure we have to change this value. So again we will have the mul instruction. Here it is 4, so blindly we can add 10, just 14. It's easy for us to write. We can see the previous iteration and we can write it. And you should also be careful not to add for the fixed ones. We see that F0 and F8 are fixed, so we should not add for these two. Then multi F20 comma F14 comma F8. Then LD F16 comma, it's like copying. You can just blindly see here. If you should not put 0, you should put 8. We should also be careful to adjust our displacement also. So then add D F20 comma F20 comma F16. Then store D 8 of R2 comma F20. So we have unrolled for 2 times. Now we are going to unroll for the third time. Third time we just add the 20 times. That means offset from this we have to add 10 offset. So we put LD F, or else we can put 20 offset here. From here you can put 20. So 22 comma Z. Instead of 0 we have put 8 here. After this iteration is over, we will call the fix-up code again. So we must have added 8 again. So we should put 16 here. 16 R1. Then multi F24 comma F22 comma, and this is a fixed, so F0. And multi F30 comma, we have F30 here, so we can put F30 blindly. That's not a problem. So F24 comma F8, and this is a fixed value. You should not change that. LD F26 comma, instead of 0 we should put 16. R2. Then add D F30 comma F30 comma F26. Then store D. Store D again 16 we have to add. 16 R2 of F30. Now while doing, now we have to do the last unrolling, that is the 4th time. Now if you put LD, then you have to add a plus displacement 10. So we will put F32, but we don't have 32 in our MIPS architecture. So what we can do is, instead of doing that, we can use the previous registers. We will see that we can see that F1 is not used here, F3 is not used here, F9 is not used here. We can see, if from this value you can see F1 is not used. We can see F1 is not used. F5 is not used. F3 is also not used. F9 is not used, and this is fixed, we don't care about that. And F9 is not used, so we can use the previous value to fix our iteration. Now if you put F1, it's like subtracting 1 here. So 0, instead of 0 we have to put, already we have called 16 iteration, so next 8 bits, after that next 8 bits you have to access, so which is 24 R1 mul D F3 we have to get F3 F1 F0. For the first time it will be difficult, but when you practice it will be easier. F9 F3 F8 LD F5, instead of 0 we have to put 24 R2, and then we have add D F9 F9 F5 and store D 24 R2 F9. Say for example the question is given for another iteration, say fifth time. Now it will be easier to add plus 10 from here. We can see that if you add plus 10, 11 is not used here. Again F13 is not used here. F19 is not used. So it will be easier for the consecutive iterations. So using this strategy we will have lot of registers we can keep track easily. So that is why adding a 10 offset would be easier while performing the register shifting. Okay, now since we have already unrolled all the loop, now we have to call the fix-up code. This is fix-up code. We are going to since we are here it is adding 8 because we are using only that particular value, and then we are going to the next value, but we are unrolled it 4 times, so we have to add it 4 8 values, that is 32. So dad IU we have to call 32 instead of 0. Instead of 8 we will change it to 32. R1 comma 32. Similarly for R2 also the same explanation goes. Now, and we have compare instruction as usual. It's saying like until and I'm encountering 800 you will do this iteration, so it's not a problem, we don't need to change that. And we have the branch equals 0 instruction, branch equals 0 R1 comma loop, and our loop is here. So this is our unrolling. We will go from this one to this one and this one. Okay, now we have unrolled the loop. Now we have to fill the VLIW process slots in such a way that it should not cause any stalls in between. So we have to do that one. So before doing that we have to note down what are the stalls it will incur for each and every instructions. That is important for us to note. So we'll just note that one also. So for floating point instruction, for a floating point instruction, there is instruction if it is producing a floating point instruction is producing a result, and floating point instruction is using that result. Say for example here F12 is say for example here F14 is a floating point instruction, multi is a floating point instruction which is used by another floating point instruction, F14 here. So this will incur a 3 clock cycle stall. Now we are for instruction producing a floating point instruction is producing a result, but a store is using it. That means 2 clock cycles. Here it is F20 is produced by a floating point instruction and used by a store instruction, and load produced used by a floating point is 1 clock cycle, and load to store we have no clock stalls. So we can fill the VLIW slots now. So to fill the VLIW slots, and in the question they have given like each and every VLIW slot will have 2 memory reference, 1 floating point operation and 1 integer operation. So we have to make sure like we have to fill such one the operations, not like 2 floating point in one places or something like that. So beforehand itself I have drawn the table. It will take a lot of time to draw the table with my pad. So I have drawn the table now. Now let's fill each and every instruction from each and every iteration. So first one is the load F2 0 of R1. It's a memory instruction. So memory instruction will go to the memory slot. So load F2 comma 0 of R1. So we filled this one. Multi F4 comma F2. F2 is produced by this load instruction and your multi is using. So load produced and used by FP, which is 1 clock cycle. So we have to make sure that one stall is given to fill this one. So multi F4 comma F2 comma F0. Okay. Now F4 is produced by multi and again used by multi. So FP producing and FP used by an FP. So we have to have 3 clock cycle, 1, 2, 3. So we will fill multi here. Multi F4 comma F2 comma F0. Okay, this is also allocated. Now load is F6. It's irrelevant of whatever instructions here. So we can schedule it in the first slot itself. We have 2 memory reference, so we can schedule it here. F6 comma 0 of R2. Okay, load is scheduled. Now this load has to be made sure that it is away, that is, this add is away from this load with 1 clock cycle, because load is producing the F6, which should be 1 clock cycle. So you will think you can fill it here, but we already have instruction. But if you see another operand F10 is sorry, here I have filled it F4, right? My bad. Okay. So here we have to have F10, sorry, F10 comma F4 comma F8. Okay, so but we see that this F10 is produced by a mul operation, which is so it is an FP producing an FP, which will take 3 clock cycles. So this add should be 3 clock cycles away from this mul instruction and 1 clock cycle away from this load instruction. Since this appears later, we should give priority to this. So we'll add 3 clock cycles, 1, 2, 3. So our add will get filled in this slot. F10 comma F10 comma F6. Okay, so add is scheduled. Now an FP is producing the result and SD is using that result. This is this scenario. So we should be 2 clock cycle away from that, 1, 2. So we'll put here. Since it's an memory reference operation, you have to fill it here. Comma F10. Okay. So we have filled for the first iteration. Now we have to fill for the second iteration. Second iteration NLD, we will put it here because the next free slot is here only. So we are putting it here. R1. Now we have scheduled this one. Now we have to schedule the mul instruction, that should be 2 cycles away from this one, 1, 2. Sorry, 1 cycles away from this, I guess. Yes, LD should be one cycle away from this. So this one. So I will fill it here. Mul D F14 comma F12 comma F0. So we have scheduled this one. Again, this mul should be 3 clock cycle away from this one. So obviously it will come consecutively. So mul D F20 comma F14 comma F8, and this load can be scheduled together here. LD F16 comma 8 of R2, and this add D obviously will come here because this mul has to have 3 clock cycle, 1, 2, 3, and we can fill the add D here. So this problem came as a simple one. It's consecutive one, but we don't know whether the stalls will occur, because we have to fill all the slots with the instruction. So we should be careful not to like fill it consecutively, and we'll have some stalls like this. See here, if it is the question is said only to unroll it for 2 times, we'll have stalls 1 2, these 2 stalls will be there, so we cannot fill those one. So we should also be careful not to have any stalls. So first we'll fill it in pencil or something, and then we can change it, so it will be simpler for while solving an examination. So now we have to go for the store instruction. Store instruction, we'll put it here, sd 8 of r2 comma f20. Now we have filled the second iteration. Now for the third iteration obviously we'll know we can fill it here. Same thing, we are going to copy R2, and I know the next load can be filled here, so obviously I will put the load here itself. But for the first time, if you do sequentially, it will be easier to do it afterwards. You can fill it directly by looking at the instructions itself. So then you can put these two mul consecutively, mul f24 comma f22 comma f0, and this mul come here, mld f30 comma f24 comma f8. Okay, now this add, we know we have a slot here, we can fill it here. Add f30 comma f30 comma f26. So we have, and this store can go here, sd 16 of r2 comma f30. Okay, so we have filled the third iteration. Now we are going to fill the fourth iteration. We have to fill it in the same way we are going to fill it. Okay, ld f1 comma 24 r1, ld f5 comma 24 r2. So these two is filled. Then multi obviously will come here. We have a slot here, so we can fill it f3 comma f1 f0. There might be a case where you will not have a slot here. In that scenario, we have to change all this iteration. We will see a problem where we have to change this iteration, we change the consecutive instructions to accommodate a slot or something like that. We will see another problem. Here it is easier for us to fill it because we are having a slot here to fill the multi from the fourth iteration. This multi will come here, f9 f3 comma f8, and this add d can come here. Add d, since it's a memory reference operation, we can accommodate a floating point, so we can execute this parallelly. Now this store has to be 2 clock cycles away, so we have to fill it in the 17th slot. So sd 24 of r2 comma f9. Now we have filled the iterations. Now we have to fill it for the fix-up code. Now we have to fill the fix-up code. Fix-up code, where we have to fill is, we have to make sure this R1 is not modified till we access. Which instruction is using the R1? The load is only using the R1. So we have to make sure that this data u goes after this load. So we have 5 to 17. We can fill data u wherever we want. This data u wherever we want here. So we have to fill. I'm going to fill it here. Okay, now we have a stored instruction. Stored instruction, we have to this store is still using the R2, so we have to allocate another slot to fill the data u. Sorry, R2 comma R2 comma 32. Now we can fill our CMPI R1 comma 800. So we'll require 20 clock cycles to finish this code. Now see, we can see that after filling all these fixed code and everything, it takes us 20 clock cycles, 17, 18, 19, 20. So 20 clock cycles it takes. So but we can leave it as it is, but if we want to decrease the number of clock cycles, we need to pull these instruction to these slots, because we are wasting these memory and floating point instruction slots, instructions units here. So we should be able to pull these integer operations here, because we have 3 slots. We can pull these 3 slots to reduce the number of clock cycles. We can reduce by 3 clock cycles. So for that we have to move this DAD-IU to here. But if we move this DAD-IU to here, then subsequent R2 instructions has to be modified in such a way that this 32 is altered, because R2 say for example our R2 is pointing to a value of 2000. Say for example R2 is pointing to 2000. Now in the 14th clock cycle I would have read 2000. In the 15th clock cycle I would have read 2008. But simultaneously in the 15th clock cycle I am modifying it to 2032. So now in the 16th clock cycle I should be writing it in 2016. But since my DAD-IU modified R2 to 32, instead of 2016 I will be adding 2032 plus 16, which will be resulting in 2048, which is our problem here. So we should alter this constant displacement value in such a way that we should accommodate all these DAD-IU here. So why this offset is hitting us? Because of adding 32. So adding 32 we have to so let's fill the DAD-IU here. So we are going to fill the DAD-IU first here. So DAD-IU R2 comma 32. Okay, so now after filling 32 we have to alter these one. We know that we are currently in 2000. This is correct, so we have to access 2016, but we are in 2032. So this 16 has to be changed to -16 so that we can reach that location. So -16, and then we can proceed as it is. We don't need to do anything, and this has to access 2024, that is 24th location. But 2020 we are already at 2032. 32 minus 24 is 8. So we have to change this displacement value to 8. This displacement value to -8. Then we would have had the if we can accommodate the DAD-IU here, and we are not wasting any slots for this DAD-IU. Now we can pull these compare and branch instructions into these slots, which results us in this schedule. Compare I R1 comma 800 and branch equals 0, R1 comma loop. So now we have reduced from 20 clock cycle to 17 clock cycles, which is far better. So this is the solution for the VLIW problem.